and I'll be majoring in dual majoring in math and physics. And here's my presentation. Come on, baby. All right. Well, you didn't need to see that slide. Okay. So I worked at Vegan Incorporated, which is a contractor of NASA. They do aerospace engineering, and they won the 1987 Minority Contractor of the Year. It's a really good place to work. I enjoyed it. So that's just a picture of what it looks like. My point of contact was David Peterson. He helped me get my feet at Vegan, and he's the Chief Technology Officer at Vegan. So he's very, very good with computers. My mentor, his name's Norm Crable, and he developed the first weather in the cockpit system using a satellite broadcast. That was one of his inventions. He invented lightning hardening systems on planes when they get struck by lightning. It doesn't affect the systems. There's no flickering or anything. They get struck by a bolt of lightning and you don't notice anything. He invented that technology, among many other things. A really great guy to work with. I really enjoyed it a lot. So when I started this internship, I didn't know anything about airplanes, aeronautics. That was then, and this is now. So it was a good 8 weeks. Before I could really get started doing research, or getting into my project, I had to do some research, learn a little bit about airplanes, fluid dynamics. So I just put some pictures in here of general things I learned. That's parts of an airplane, flow fields. This just shows downwash of an airplane, what it's like when planes fly in similar ranges, and what happens if a plane follows behind a bigger plane. What happens is you crash. But just general stuff. This shows stall on the right and on the left tip vortices. But really, what I found with my research is you learn science and you practically can work magic. You give me just about any object, and just stuff that they taught me, not stuff that I figured out, just things that other people have already learned. I can make it fly. Give me a rock, I'll make it fly for you. And make things fall slower, pretty much whatever you want, and that's really cool. It makes you feel like you got some power under your belt. So in terms of my actual project, what I worked on, to give you a general idea first, it's called the ARIS. It's the Active Ride Improvement System. And what it does is it can be used for all aviation, and it makes planes fly with less movement. It's called wind gust mitigation. And so when a wind gust hits an airplane, what the Active Ride Improvement System does is it makes it so that it doesn't move as much. It's safer, it's better, there's less wear on the airplane. As to how it works, I'll get into later, but for what it looks like, that's Norm Crable, and there's the Active Ride Improvement System. So that's the actual model. With all the research, all the experiments I did, that's the model we use. We use that in a wind tunnel, Vegan's wind tunnel, and that just gives you an idea of what it looks like. But in order for the tests on the model to be run, first we had to be able to make sure that the setup of the wind tunnel worked, and that it would give plus or minus 3 degrees of gusts hitting the aircraft. So that job was given to me, and so this is just a picture of the general outline for the ARIS, the Active Ride Improvement System. But in order for me to find out, hey, will this system work? Can we get that plus or minus 3 degrees of wind gusts hitting the model? I had to work with a program called JavaFoil, and what it does is it simulates airflow using this setup right here. So I would make a wind foil or an airfoil for the exact specifications that they told me. And you can see at the top, you can see, the mouse doesn't work, but you can see the tabs at the top. And so you can pretty much alter anything about it. So this is a flow field. If you pick any point on there, I can find the velocity vectors at that point, find exactly what's happening for the wind at that point. So if you had 2 wings, and the wing in the bottom left was one wing and there was another wing above it, then I could find what's happening with the air at that point. The configuration that I was working with, this is just a diagram I made up just to give you an idea. On the left would be the wind tunnel, so the wind is passing that way, and the wind tunnel would be over here. And then on the far right you see the model, and there was a wind vane that we were reading from. So when I ran the calculations using JavaFoil, I found at the top you can see that alpha sign, negative 0.701 degrees. Well, we needed plus or minus 3 degrees, and I found that it was less than that. So what I actually did is came up with a second position to place the wind pool that was creating those gusts. And you can see position 2 at the bottom. The alpha is plus or minus 4.5 degrees. So we get the plus or minus 3 degrees we need. My work was useful. It helped them out. And they appreciated it. I felt like I was good for something. It was a good experience. So in conclusion, use position 2. As for the main project, so that was just background. That's things I did to kind of get my feet at VGON. When I really jumped into the science, I worked on a test called the turbulator test and a test called the sting load test. This is 2 of the 12 tests, and I only mention that because I want you to get an idea of Norman Crable. His mind is so expansive that for one model, he has 12 experiments, and each one is not independent, it's dependent on the results of the first one. So if the results of the first one don't yield what he expects, he changes the next 11 experiments, and it's all in his head. The whole thing is this massive web of just pure intelligence. I don't know any other way to describe it. This is the model setup. So you can see the braces. Those were initially not there. They were added as the wooden blocks were added as a request of mine. The braces were added as a request of Norm and a guy I worked with named Mohit. And what we did is we made the whole structure much more. It didn't vibrate as much. But okay, for the actual turbulator test, so what Norm calls a turbulator is an oscillating airfoil in a flow field which causes turbulence. So it just moves back and forth, you get a sine wave. That sine wave then moves the wind vane that's on the model. And so you can see what happens on the wind vane relative to the frequency that the turbulator is moving. So this right here, it's a calibration curve. And the reason I put this in here is because something I learned at VGON was that when you conduct an experiment, you don't just go in, run the experiment, and leave. There's calibration. There's many things that you have to do. So I wanted to put this graph in here to show that, hey, before we can just jump in and do science, you have to get ready for science. You have to build the model. That takes days. You have to take voltage and be able to convert it into angle, because we needed angle, but you can't just get volts and just go from there. So I wanted to include this to just show you that, and this is one of the main things I learned, is that this is real science. It's not just something out of a book, which is really cool. When we actually ran the experiment, this is frequency at 5 hertz. It shows you a decent sine wave, but this was it at 10 hertz, and you can see there's nothing. This was at the position 1. So it's good because when I did the calculations with Java foil, I found that position 1 didn't really produce what we needed. When we went on and ran the experiment at position 1, due to time constraints with moving to position 2, we went on and ran at position 1, and we found exactly what I found in the calculations. So that's cool. All right, we ran calculations, we used equations, and then exactly what we predicted happened in real life. So it's neat. What we're learning, it works. Here's the average angle of attack for each frequency. And you can just see, the main thing to see with this is that it's based around 1, and we needed plus or minus 3. So you can see, again, position 1 wasn't strong enough. So the conclusion, same as Java foil, we need to move to position 2. That hasn't been done yet because it takes a lot of time, but we now know where to go. The sting load test was the second test that I worked on, and what we did was we would put weight up to 8 pounds on the model, and we would find out what the deflection was on the model. This gives us an idea for when wind hits the model, how's it going to affect the model. So I wanted to show the setup again. I'm not sure if there's a laser pointer, but if you can see on the metal on the model, there's a little brace on top and on the bottom. So we would pull on that up to 8 pounds, which we measured, and then we would see the oscillation of the model. So how's the test work? This is some general results, but I'll just walk you through them using pictures. So the data comes out. This is a graph directly from the instrument that we use to measure it. It's called an oscilloscope, and it measures voltage versus time. So we can use this graph and then use calculations, which we can get from an FFT plot, which is a fast Fourier plot. And what it does is it gives you the natural frequencies that occur within the system. So you can see the large curve. What it does is it shows you whichever one's the biggest curve, that's the main frequency in the system. And you can see that about 7 hertz was the curve. It was 6.8315. And over there we had another curve at 27 hertz. Oh, thanks. Okay, cool. So right here you can see that we've got this second natural frequency. So we know there's something wrong. The system's oscillating like this. It's going back and forth. It's moving at 7 hertz. But why are we getting this? So that's science. We got to find out. We went on and used these results. and we get this curve. And you can see right here, you can see that extra frequency in there. It's messing up the data. So what we did is we actually ran a cutoff where you can cut off all frequencies above 10 hertz. So that gets rid of the 27 hertz, and you get this data. Well, that looks good. Well, we decided, hey, we want to be able to get this data directly from the instrument itself. So what we did is we added these braces. And that's what I was mentioning earlier, that these weren't originally on there. We added these boards. All of this removes, it doesn't allow the system to vibrate. And so the only thing moving is this going up and down. And then this is the data that we got. And that's good data, right? That's beautiful. So I know, hopefully it's not too boring to look at just a bunch of dots, but that's 3 weeks of work that made that data look that good. So what we find, basically my work, what it did is it helped them to get set up to finish this experiment. It got the procedure, everything's laid out, and I had a written report which I presented to them, which it'll allow them to finish up the sting load test and move on to experiment 3. In terms of personal influences that this internship has had on me, with career directions, it's definitely shown me that my work actually matters. What I did in the lab, it wasn't just reading and writing. There was, my science, it mattered. And like I said, I went in there and I didn't know anything. I really didn't know. I just knew aeronautics as airplanes. And now I feel like I could practically put wings on and fly myself. So it's good stuff. With future plans, as I mentioned, I'm going to Vanderbilt University, so I'll definitely stick with math physics. This has also kind of interested me in aerospace. Obviously, if you work at NASA, you think big, you think astronauts. And as everyone else mentioned, there's a lot of stuff going on, but I couldn't help but get kind of sucked into the whole astronaut thing, and I'm definitely very interested in it now. So it's definitely somewhere else I might go. And as for NASA, I certainly want to look at the other centers. I want to see everything NASA has to offer, because I just got a taste here at Langley, and it was a good taste. So I want to see the whole cake. So I want to put a little disclosure in here that this presentation doesn't match the original outline. And I know you guys didn't get to see the original outline, but I just thought it was important to mention that something I learned with real science is that things don't come out the way you expect them to. You have to spend extra time on tests that you never thought would have taken 3 weeks, when it was just simply measuring deflection. So why does it take 3 weeks? Well, there's all sorts of things you have to measure, and if you put in the plan that, hey, this is going to take 2 days and it takes 3 weeks, that's good. That means what you're doing, you're making things work, you're making things better, and you're doing science. And that's good stuff. So I hope you enjoyed the presentation, and I'd like to introduce Katrina Paulini.